Hydrocarbon processing involves a series of chemical and heat processes to convert raw materials into an array of essential products such as gasoline, kerosene, olefins, rubber, and plastics.
At the heart of these processes are fired heaters, commonly called furnaces. These furnaces are used with many processes, including distillation, reforming, olefins manufacturing, and hydrocracking. As the operator, it's your responsibility to operate your furnaces as efficiently and safely as possible. The objective of this program is to provide the basic concepts of safe and efficient furnace operations.
Efficient furnace operation has become a major concern with the rising cost of fuels. Today, fuel for processing is about 2/3 of the total utility cost. Most of this fuel is used in fired heaters.
Environmental regulations have also made it necessary to closely monitor emissions from furnaces and other processing equipment. In this program, we'll cover the principles of heat transfer and combustion, furnace equipment, performance monitoring, startup and shutdown, and troubleshooting. Fired heaters are used to transfer heat. In the furnace, heat is produced by the combustion of fuel at the burners. This heat is then transferred to the process fluid that circulates through the tubes of the furnace. There are three methods of heat transfer: radiation, convection, and conduction. Radiation is the means by which heat is transferred from the sun to earth. Radiant heat travels in waves, as light does. For this type of heat transfer to occur, the object being heated must be in direct line of sight with the source of heat. As with visible light, these radiant heat waves can be reflected. In a furnace, the tubes that are exposed to direct heat from the burners are called the radiant tubes. Heat is transferred to these tubes primarily by radiation. A second method of heat transfer is convection. Convection involves a flow of gas or liquid to carry heat. A central heating system uses this type of heat transfer to distribute heat throughout a room with a flow of hot gases. In a furnace, the tubes that are located above and out of sight of the burners are called the convection tubes. As hot gases rise to go out of the stack, they transfer heat to these tubes. This design increases furnace efficiency by allowing more heat to be used before it escapes out of the stack. The third method of heat transfer is conduction. Conduction is the way that heat is transferred through solids such as metal or glass. This is how heat is transferred through the metal tubes in the furnace to the process flow inside. When heat reaches the process flow inside the tube, a convection current is set up that transfers the heat throughout the liquid in the tube. So there are three different ways that heat is transferred in any furnace: radiation, convection, and conduction. But what determines how fast or how much heat is transferred? While there are several different factors that affect the rate of heat transfer, the most important one is temperature difference. In order for heat transfer to occur, there must be a temperature difference between two substances. The greater this difference is, the greater the rate of heat transfer. Many of the factors that affect the heat transfer rate are due to the design of the furnace and are beyond your control. However, later in the program, we'll look at some of the things you can do to improve the efficiency and utilization of heat transfer in your furnace. Right now, let's consider how heat is produced in a furnace. This is accomplished by a chemical reaction called combustion. For combustion to occur, three things must be present at the same time and in the proper proportions: fuel, air, and a source of ignition. The fuel used in a fired heater may be natural gas, fuel oil, or a combination of gas and oil. Natural gas is preferred in many installations because it is cleaner and burns more consistently than oil. Air is needed for combustion because it provides oxygen that reacts with the fuel. The final thing needed for combustion is a source of ignition. The ignition source provides the heat energy that is required to start the combustion reaction. In the operation of a fired heater, it's important to maintain the right proportion of fuel to air. When this is done properly, combustion will be complete and the maximum amount of heat will be generated without any fuel waste. Incomplete combustion occurs when there's not enough oxygen available to burn all the fuel. When this happens, unburned fuel can accumulate in the furnace, which is a potentially dangerous situation. In addition, incomplete combustion drastically reduces the production of heat. One of the challenges to the operator is to provide enough oxygen to the furnace to allow complete combustion while at the same time minimizing excess oxygen to assure efficient use of fuel. The key to safe and efficient furnace operations is controlling the combustion process. In an emergency situation, it might be necessary to quickly shut down the furnace. The best way to do this is to remove the source of fuel.
We have seen that by controlling fuel, oxygen, and heat, the operator can control combustion in the furnace. Now stop the videotape and turn to section 1 in your workbook for a review of heat transfer and combustion. Make sure that you work through these exercises as they contain information not covered in the video that you'll need to know as the program progresses. Furnaces are custom designed to control the flow of heat and handle the load needed for the process they service. The one shown here is one of the more common furnace designs.
This type of furnace is shaped like a house and is called an A-frame or cabin furnace. The inner walls of the furnace are lined with a material that reduces heat losses and reflects heat back onto the tubes. This material is called a refractory lining. The burners in this design are located on the floor. They can also be placed on the walls or the arch of the furnace. The air required for combustion enters the furnace through air registers located directly under the burners. The section directly above the burners is called the firebox. The firebox contains the flames in the furnace and does not let any unwanted air into the combustion zone. The radiant tubes are located in the firebox of the furnace. They're in direct line with the burners, so they receive most of their heat by radiation. The section of tubes above the burners is called the shock bank. These tubes receive both convection and radiant heat. Above the shock bank is the convection section, sometimes called the economizer section because it extracts heat that would be otherwise wasted. The tubes in this area are heated by the hot flue gases before they leave the furnace stack. The process flow is sent through the tubes and is quickly heated. It then flows out of the furnace to other process equipment. The tubes which carry the process flow are generally divided into passes or coils. If the passes are balanced properly, each pass receives the same amount of process flow and absorbs the same amount of heat. After the process flow is circulated through the passes, it is rejoined at the outlet. In the stack of the furnace is the damper. The damper adjusts to control the flow of hot gases out of the furnace. This upward flow of hot gases is known as the furnace draft. Now let's see what happens in our simple model of a furnace. The air registers are open to provide the correct amount of air for combustion. The damper is adjusted for the correct amount of draft. The feedstock is pumped into the furnace and divided between the passes. After circulating through the tubes of the furnace, the feedstock is rejoined at the outlet of the furnace. There is a target outlet temperature for the process flow, and this is used to determine the amount of fuel going to the burners. In an automatic control scheme, the outlet temperature is monitored by a temperature controller, which controls the flow of fuel to the burners. In order to increase the outlet temperature, more fuel is burned. To decrease outlet temperature, less fuel is burned. The furnace draft is important because it moves hot flue gases out of the stack and draws fresh air through the registers to the burners. The type of furnace we've discussed so far is a natural draft furnace. It's given this name because the draft occurs naturally due to the fact that hot air rises. The rising flue gases cause the pressure inside the furnace to be slightly lower than the pressure of the atmosphere. This lower or negative pressure is what maintains the draft through the furnace. Other furnaces use fans to maintain a draft. In an induced draft furnace, a fan is located in the flue gas ductwork to the stack. This fan pulls the flue gases out of the furnace to maintain an adequate draft. A forced draft fire heater uses a fan to supply air for combustion. Even though the combustion air is under positive pressure, a negative pressure is maintained in the rest of the heater by the natural draft of the hot flue gas. Fired heaters, which use both forced and induced draft fans, are called balanced draft furnaces. In this system, a forced draft fan supplies air for combustion, while the induced draft fan pulls the flue gases from the firebox to maintain a negative pressure in the furnace. Preheaters are used on some fired heaters to reduce fuel consumption. These systems use the heat carried by the flue gases, which otherwise would be exhausted to the atmosphere, to preheat the air for combustion. This conserves energy because the combustion air enters the furnace at a higher temperature and therefore requires less heat for the combustion reaction. An essential piece of equipment in any fired heater is the burner. The function of the burner is to mix fuel with air in a manner that will maintain stable and continuous combustion. The design and operation of a burner will vary depending on the type of fuel that is being used.
Let's take a closer look at how burners work and review the material on furnace equipment. Stop the tape and turn to Workbook Section 2. In order to obtain the best results with a fired heater, key variables from both the process and combustion side of the furnace must be closely monitored.
And the furnace itself must be physically inspected to make sure it's operating properly. This segment of the program will focus on these key operating variables and the related furnace inspections. An important factor in operating a furnace is controlling excess oxygen. There must always be enough oxygen in the firebox to ensure complete combustion. Too much oxygen, however, wastes heat because extra fuel is used to heat the surplus air in the furnace. Excess oxygen is the most important variable affecting furnace operating efficiency. The amount of oxygen in the furnace is monitored by an oxygen analyzer. Most furnaces operate between 1 and 5% excess oxygen, depending on the design of the furnace. The air registers are the main control of air to the furnace. When the furnace is lit, the air registers should be adjusted to allow the proper amount of air to each burner. The air registers on out-of-service burners should be closed to prevent excess air from entering the furnace. Peepholes should also be kept closed to prevent excess air from entering the furnace. Another important variable that must be monitored and controlled is the furnace draft. The draft is controlled by adjusting the stack damper to maintain a slight negative pressure inside the furnace. Measurements are usually taken at 3 points in the furnace to monitor the draft. The indication of draft is a negative pressure reading at each of these points. Process flow rates are another key operating variable. The flow rates through each furnace pass, for example, must be kept balanced to assure even heating of the process fluid and to avoid tube damage due to overheating. The pass inlets and outlets are usually equipped with temperature, pressure, or flow instruments that allow an operator to monitor the situation and keep the passes balanced. Product outlet temperature is the temperature of the process flow as it leaves the furnace. Normally, there is a set temperature or range of temperatures that must be maintained. To change the outlet temperature, you either increase or decrease the amount of fuel going to the burners. When you adjust the fuel rate, however, You must also change the amount of air going to the burners to ensure safe and complete combustion. Some furnaces are equipped with automatic controls to perform these functions. If the furnace is not equipped with these automatic controls, the operator is responsible for controlling the air and fuel flow for combustion. Another variable that tells you a great deal about the operation of your furnace is the stack temperature. The stack temperature indicates the amount of heat that is lost from the furnace. While it's desirable to keep this temperature low, it shouldn't be lower than the condensation point of the flue gases. This is because flue gas condensation can cause corrosion in the stack. A high stack temperature or rapid increase in temperature often indicates a problem in the furnace, such as a leaking tube. Problems in the furnace can sometimes be detected by analyzing the flue gas for oxygen. If the flue gas from the radiant section of the furnace contains excess oxygen, this indicates that too much air is entering through the air registers, wasting heat. Too much excess oxygen at the outlet of the convection section may indicate that air is leaking into this part of the furnace. While it's possible to monitor much of the furnace activity from the control room, it's also necessary to physically inspect the furnace during operation. The header box houses the tube end fittings outside the main case of the furnace. Smoke coming from the header box indicates a tube leak. Another indication of this problem would be smoke rising out of the stack. Never open the doors of a leaking header box while the furnace is in operation, because a flash fire could result. Pilots should be lit at all times while the burners are firing, and they should be checked on a routine basis. If a pilot goes out, it should be repaired and relit. Flame pattern should also be inspected on a regular basis. The flame should be bright and clean with no trace of smoke. A properly burning gas flame is blue and compact, while an oil flame tends to be bright yellow. Flame should not touch the tubes. This is called flame impingement. Flame impingement can quickly damage a tube and cause it to rupture. The fire should always be kept as uniform in length and size as possible. Let's look at some other undesirable flame patterns and consider the causes. A long, smoky flame is caused by insufficient combustion air or insufficient atomizing steam. The flame may be shortened by increasing primary or secondary air or by increasing atomizing steam. A thin, fluttery oil flame indicates too much atomizing steam is being used. A reddish, dusty flame with smoke over the bright part of the flame indicates a lack of oxygen for complete combustion. Sparks in the flame could be caused by a dirty burner tip, wet steam, solids in the fuel, water in the fuel, or improper oil atomization. A dazzling white flame indicates too much excess oxygen or too much atomizing steam. Check your fuel pressure, especially when lighting the burners. Too much pressure will cause the flame to lift off the burner. Too little pressure, on the other hand, will cause the flame to blow back into the burner. Erratic flame pattern and a puffing sound from the furnace indicates loss of draft and a serious shortage of oxygen. The flames may start burning out of the heater in cracks where air enters. This is a hazardous situation which can damage the furnace. Puffing and woofing can also be caused by flame instability due to burner damage or by too high a fuel pressure.
It's time for a review of the material and monitoring furnace performance. Stop the tape and turn to Workbook Section 3. Every plant has its own set of procedures for furnace startup. The general procedures outlined here are designed to provide an overview of furnace startup. However, each operator should carefully follow company procedures for his unit.
There are 5 major steps to furnace startup: pre-startup inspection, purging the furnace, lighting the pilots, lighting the burners and placing the furnace in normal operating mode. The first step in the pre-startup inspection is to check that the pilot and main fuel systems are blinded and that the fuel supply for each burner is closed. Then inspect the furnace to assure that it is ready for startup. This involves inspecting the furnace to make sure it's clear of debris, checking the burners, and making sure all the furnace doors are closed. The damper and burner air registers should be fully open during startup so that the furnace can be adequately purged with air or steam. Purging clears the furnace of any combustibles and starts a draft. Purging will usually last a minimum of 15 minutes or longer, depending on the size and type of furnace you're dealing with. While the furnace is being purged, you can start the process flow through the coils and balance the passes. This circulation must be established before you light any of the burners. Before starting the lighting procedure, you may be required to put on special protection light-off gear. Check your safety regulations to see if this equipment is needed. The next step in the lighting procedure is to check that all fuel gas valves are shut tight and then remove the fuel gas blinds. Each pilot must be lit separately. Light a pilot at each end and then one in the middle to provide a source of ignition throughout the furnace. Once all the pilots are lit and burning steadily, you're ready to light the burners. Light the burners in the same order as you lit the pilots. Slowly open the fuel gas valve to ignite the burner. If the first burner does not light, close the main fuel and pilot valves and re-purge the furnace. Then restart the lighting procedure. As the burners are being lit, you adjust each air register for the proper amount of oxygen and the proper flame pattern. Then you adjust the damper for the proper draft. During the light-off procedure, it's also important to monitor the fuel pressure and keep it stable. Since the fuel flow is on manual at this time, there will be a tendency for the pressure to drop as you light additional burners. After lighting the burners, gradually increase the fuel so that the furnace is slowly heated up to the desired outlet temperature. It'll be necessary to make further adjustments for draft and excess oxygen until the desired conditions are achieved. When the target outlet temperature is reached and the passes are balanced, place the controls on automatic. The furnace is now in normal operation. Normal furnace shutdown procedures involve gradually reducing the temperature of the furnace to avoid damaging the equipment. Again, every company has its own detailed procedures. The general procedures are outlined here to provide an overview of the process. During normal shutdown operations, the process flow rate and firing rate are gradually reduced together. When minimum firing has been reached, you shut off fires and open the PEEP doors. Process circulation is continued to cool down the tube slowly. Next, you open the stack damper and air registers to purge the furnace. Then block the fuel systems, including the burner and regulator valves. And when the furnace is cool enough, stop the process flow and block the process systems. Next, you purge the process tubes with steam. Each individual pass must be purged. After purging, make sure all burners are isolated and that all main and pilot fuel headers are blinded. This completes the normal furnace shutdown operation. Some abnormal situations may call for an emergency furnace shutdown. Under these circumstances, the burner fuel is stopped immediately and the process flow may have to be dumped. You should be familiar with your company's emergency procedures so that you can quickly shut down the furnace in the event of trouble.
Let's review the material and furnace startup and shutdown procedures. Stop the tape and turn to Workbook Section 4.
When an emergency situation occurs, you should be prepared to respond quickly and correctly. Furnaces have unique problems, some of which may be detected only in the field. Correct diagnosis of the problem as well as quick response is important. In this segment of the program, we'll consider both the symptoms and solutions to these common operating problems. Let's start with flame impingement. Flame impingement occurs when the flames are actually touching the metal surfaces inside the furnace, usually the tubes. This contact weakens the metal and can quickly plug up a tube with coke deposits. Flame impingement can sometimes be corrected by adjusting the position of a burner or by pinching back the fuel supply to the problem burner. If these adjustments don't correct the situation, it may be necessary to remove the burner for cleaning or repair. A hot spot in a furnace is an area that has become overheated due to an improper distribution of heat or flame impingement. Hot spots may occur on the tubes, the refractory, or even on the outside skin of the furnace. They're a problem because they compromise the strength of a metal and cause coke deposits. Some hot spots can be detected with the human eye as a glowing red spot on the metal. In other instances, special heat-sensing instruments such as a pyrometer or an infrared scanner are used to detect hot spots. Sometimes hot spots on the furnace tubes can be corrected by redistributing the process flow so that the hotter pass of tubes receives more charge. The increased flow of charge absorbs more heat and carries it away from the hot tubes. In other situations, it may be necessary to reposition a burner or remove it from service. Another common furnace problem is the buildup of coke in the tubes. A certain amount of coking occurs naturally due to the presence of carbon particles in the process flow. High temperatures, however, aggravate the problem by increasing the amount of carbon deposits. The coke acts as an insulator, so less heat is transferred to the process flow and more heat accumulates in the metal tube. If the coking is severe, the tube may eventually rupture due to the excessive temperatures. A furnace can be decoked by injecting superheated steam and air through the tubes. This operation burns off the coke and cleans out the tubes. A disadvantage of this operation is that it interferes with the ongoing processing because the process flow must be removed from the tubes during cleaning. In furnaces which burn oil, an ash deposit or soot gradually accumulates on the outside of the convection tubes. These deposits must periodically be removed because they interfere with heat transfer. Some furnaces are equipped with stationary soot blowers, which are long tubes that run through the convection section. Steam is circulated through holes in the soot blower to blow off any accumulations of soot. A second type of soot blower is the retractable type. It's a steam lance that is taken out of the furnace when not in use. This type of soot blower can be programmed to automatically blow selected tubes in any given sequence. Soot blowing can be done while the furnace is in operation. However, it may be necessary to completely open the damper to prevent the steam and falling soot from snuffing out the flames. It's important to closely monitor and maintain the excess oxygen and draft during soot blowing. Furnace equipment like pumps, fans, valves, and burners can and does occasionally fail. When this happens, an operator must be prepared to respond quickly to prevent damage to the furnace or a possible accident. The feed pump circulates the process flow through the furnace. If this pump fails, the circulation will stop and the furnace will immediately start to overheat. This can damage the tubes and refractory and cause severe coking. Your first reaction should be to restart the pump if possible, or go to a spare. If you can't get the flow started immediately, you'll need to stop the input of heat by cutting off the fuel to the burners. The damper should be opened fully to allow the maximum amount of heat to leave the furnace. And steam should be added, which will have a cooling effect on the furnace. By cutting off the fuel and removing as much heat as possible, you minimize the chances of furnace damage. Once the situation stabilizes, you would want to call in maintenance and have the defective pump repaired. A second type of equipment failure is a fan failure. If one of the fans in a balanced or induced draft furnace fails, this will result in a loss of draft. If the furnace is equipped with natural draft air doors, the flame safety system will automatically open the doors, and it may be possible to keep the furnace operating at a reduced load. Some furnaces are equipped with steam rings that discharge steam into the furnace in the event of a fan failure. The hot steam rises upward and creates enough of a draft to allow continued operation. But if air doors or steam rings are not available, the safety system will automatically cut off fuel to the burners and the furnace will have to be shut down. A valve failure is a third type of equipment problem. If the valve is controlling the process flow, it will usually fail open or become stuck in one position. In either case, you won't be able to adjust the rate of flow. If a bypass valve is available, you may be able to avoid a shutdown by routing the flow around the failed valve. When a valve in the fuel system goes down, it usually fails in the closed position. This stops combustion in the furnace and means a shutdown. The furnace burners can also break down. Burner failures are often caused by plugging or fouling in the burner tip. If a burner fails, you'll need to remove it from service for cleaning or repair. Instrument failure is not always easy to detect. The operator must understand the interaction of variables in the furnace to judge whether a particular reading is accurate. If the furnace has automatic controls, the controls may try to correct a situation which doesn't exist. If this happens, the operator must take the controls off automatic and manually adjust the operating variables. Correct diagnosis and quick reaction can often prevent a furnace shutdown. Let's consider an example. In an automatic system, the controller adjusts the fuel flow to the burners based on the outlet temperature of the charge. Now, if the measuring or transmitting instrument sends out a faulty low temperature signal to the controller will automatically increase the flow of fuel to the burners, trying to compensate for the apparent decrease in outlet temperature. This, in turn, will cause the furnace to overheat and could cause coking in hot spots. If the operator suspects this is occurring, he can check the individual outlet temperatures for each pass of tubes. If these are above normal, this would indicate that the measuring or transmitting device has probably malfunctioned. The operator would then manually control the amount of fuel to the burners to prevent the furnace from overfiring. Another furnace problem is flameout. This is a situation where the burner flames go out, but the fuel is still entering the burners. When it happens, there is a dangerous buildup of unburned fuel in the furnace, which poses a threat of explosion. So the furnace must be immediately shut down and purged. A flameout can be caused by several things, such as a loss of draft, too much fuel, or not enough oxygen entering the air registers. In a situation where oxygen is decreasing and the amount of combustibles is rising, it may be possible to correct the problem before a flameout occurs. This can be done by decreasing the flow of fuel to the burners, opening the damper to increase draft, or by opening the air registers to increase oxygen. But if you're unsure how much uncombusted fuel is in the furnace, the safe thing to do is proceed with a furnace shutdown.
In this program, we've covered the basic principles of heat transfer and combustion.
We introduced you to furnace equipment and discussed its operation, and provided some basic guidelines for furnace startup and shutdown. We also looked at what you, the operator, can do in terms of performance monitoring and troubleshooting to make the operation safer and more efficient.
We hope that this program will help you in your day-to-day operation of fired heaters. Thank you for watching.